Hello viewers, welcome to my video series on biomolecules. In the last video we are talking about carbohydrates. We defined carbohydrates and I presented the chemical definition of carbohydrates, that carbohydrates are polyhydroxyaldehydes and ketones, and I furnished two examples of simplest carbohydrates. In this video we are going to discuss the classification of carbohydrates and then we will see some important features of carbohydrates and their nomenclature. So let us see, first let us see the classification of carbohydrates. Carbohydrates are classified into three major classes. First is monosaccharides, second is oligosaccharides, and third is polysaccharides. Monosaccharides, as the name implies, mono means one and saccharides is derived from the word saccharose, that means sugar. So they are the simplest sugar. Monosaccharides are the simplest sugars. They are unit sugars which are used to form all other kinds of sugars. So we have monosaccharides, here we can see their properties. First is that they cannot be hydrolyzed. Second is that they can be reduced by several reducing agents such as failing solution, etc. And they are classified into two categories. One is aldoses and another is ketoses. This I explained in my last video. If they are polyhydroxyaldehydes, they are classified as aldoses. So aldoses have one aldehyde group along with several hydroxy groups, and ketoses are having a ketone group, that is CO group, along with several hydroxy group. So if a carbohydrate is having an aldehyde group along with several OH groups, it is classified as an aldose. So now we classify aldoses into different classes on the basis of number of carbon atoms. So if an aldose is having 3 carbon atoms, then it is called triose. So a triose is an aldose having 3 carbon atoms, and an example is glyceraldehyde, which is the simplest sugar. Then if an aldose is having 4 carbon atoms, it is tetrose, like erythrose or threose. Then monosaccharides having 5 carbon atoms are pentoses, and their examples are ribose and raffinose. Every one of you must be familiar with ribose because it's a constituent of RNA, and a related sugar deoxyribose is a constituent of DNA. Then coming to hexoses, these are the most common monosaccharides that you may be familiar with. They are 6 carbon aldoses, and their examples are glucose and galactose, etc. Along with this series, we have a parallel series of ketoses. These are monosaccharides having ketone group, so they are polyhydroxy ketones. And in this we have trioloses, tetraloses, pentuloses, and hexuloses. The difference is that while aldoses end with suffix ose, O-S-E, ose, they end with, the names of aldoses end with ose, so they are suffixed with ose. Trioloses end with ulose. The names of ketoses end with ulose, just like triolose, tetralose, pentulose, hexulose, heptulose, and so on. The second category of carbohydrates is oligosaccharides. Oligo means few. So these are carbohydrates having few sugar units. So they are formed by linking of 2 to 10 monosaccharides, and they are linked through bonds called glycosidic bonds. So glycosidic bonds are bonds that link sugars together. Their properties, one of their properties is that they can be hydrolyzed. So if there are 2 sugars in an oligosaccharide, so on hydrolysis it will yield 2 sugar units, 2 monosaccharides. And if there are 3 sugars linked together, then on hydrolysis it will yield 3 monosaccharides, and so on. So they can be hydrolyzed, and the second property is that they can or cannot be reducing. Unlike monosaccharides, which we are all reducing sugars, these sugars can be either reducing or non-reducing. For example, sucrose is a non-reducing sugar, whereas maltose is a reducing sugar. Again, these oligosaccharides are classified on the basis of number of sugar units linked together. So we have disaccharides in which two monosaccharides are linked together. Their examples are maltose, sucrose, that is table sugar, the common sugar that we use in our tea, and lactose. Lactose is the milk sugar. This is also a disaccharide. Then trisaccharides are having three sugars. The examples are Raffinose or Gentianose. Tetrasaccharides have four monosaccharides linked together. Examples are Stachyose or Scorodose. And similarly, pentasaccharides are oligosaccharides having five monosaccharides linked together. So after oligosaccharides, the third and last category of carbohydrates is the polysaccharides. They are polysaccharides means they are having many monosaccharides, because poly means many. So they are having many monosaccharide units joined together through glycosidic bonds. Their important feature is that they are non-reducing sugars, and they are classified into two categories. One is of homopolysaccharides and another is of heteropolysaccharides. They are called homopolysaccharides if they are formed of only one type of monosaccharide units bonded together. And their examples are amylose means starch, glycogen, cellulose, chitin, inulin, etc. Then there are heteropolysaccharides. These are polysaccharides which are formed of more than one type of sugar units linked together. For example, we have hyaluronic acid, termeton sulfate, or keraton sulfate, and so many other types of polysaccharides exist, which are made up of alternating sugar units. So they are called heteropolysaccharides for this reason. Towards the end of this, I'll explain one more term, and that is very frequently used. Students, you might have read about mucopolysaccharides. So mucopolysaccharides are polysaccharides which have nitrogenous sugar in that. So one example is chitin. Now let us start with the first category of carbohydrates, that is monosaccharides. As I said earlier, that they are grouped into two categories, aldoses and ketoses, which are again classified on the basis of number of carbon atoms. So in aldoses, we have the simplest aldose, which is a 3-carbon sugar, triose, and I earlier wrote its structure. This is glyceraldehyde, and a corresponding monosaccharides in the ketose series is this CH2OH, CO, which is dihydroxy acetone. So this is the simplest aldose and this is the simplest ketose. Now we can add carbon atoms to get tetroses, pentoses, hexoses, and so on by adding carbon atom. For example, if we here we have 1, 2, 3 and 4 carbon atoms, and this is an aldehyde group. So this is a tetrose sugar. Similarly, we can have pentose, this is a pentose sugar. The carbon atoms are numbered like this, and this sugar is ribose. In the same manner, we can get hexose by adding one more carbon atom. Similarly, in the triolose, if we add one more carbon atom, then we get something like this. So this is a 4-carbon ketose, that is tetrolose. By adding one more carbon, we get 5 carbon ketose, that is pentulose. Here you see ribulose. This sugar is ribulose. By adding more carbon atoms, we can get higher orders of monosaccharide. Here I show you one very famous method of chain elongation that is used in monosaccharides. This method is called Killiani-Cyanohydrin synthesis. What we do in this method is that first we react with hydrogen cyanide HCN, and in the next step we perform hydrolysis with the removal of ammonia. In the third step, another water molecule is removed in lactonization step, and in the last step reduction reaction is performed. So as you can see, if we start with a 3 carbon sugar, we end up with 4 carbon sugar. Here in this case, for example, we started with diglyceraldehyde, which is having 3 carbon atoms, and we ended up with 4 carbon sugars, that is erythrose and threose. Here you can see that we are getting 2 different isomers after performing cyanohydrin synthesis. Now let us see the phenomenon of optical isomerism in monosaccharides. But before that, I would like to remind you what is isomerism and what are its types that you might have studied in chemistry. As you know, that isomerism is the existence of many forms of a chemical with a particular formula. It is broadly classified into 2 types: structural isomerism and stereoisomerism. Whereas structural isomerism arises due to variation in chain length, variation in the position of substituents, or variation of functional groups. The stereoisomerism is due to difference of spatial orientation of a molecule, and this stereoisomerism is of 2 types. One is geometrical isomerism, that is due to rotation around a double bond, rotation of groups around a double bond, and second is optical isomerism. So this optical isomerism is extremely important for understanding the nomenclature system of monosaccharides. Now let me tell you about the phenomenon of optical isomerism. See, in this phenomenon, optical isomers differently rotate the plane of polarized light. As you know that ordinary light is having the oscillations of light wave, that is electromagnetic wave, in all the directions. But when this ordinary light is passed through a polaroid, so what it does, it cuts off all the radiations, all the vibrations in different planes, except in a particular plane. When this plane polarized light, which is having oscillations of electromagnetic wave in only one plane, is passed through an optically active solution, it is rotated differently. Either it is rotated towards the right, in that case it is called the isomer is called dectorotatory, or it is rotated leftwards. In that case, the optical isomer is called levorotatory. So far as the basis of optical isomerism is concerned, this phenomenon arises due to the presence of asymmetric carbon, which is also called chiral carbon. A chiral carbon is one that is having 4 different groups attached to it, and when such a chiral carbon is present, then the mirror images are non-superimposable, and this non-superimposability of mirror images give rise to enantiomers. Here you can see an illustration of what I just said. Here you have a mirror. This carbon is having 4 different groups attached to it. So this is a chiral carbon, and in order to mark a chiral carbon, we usually put an asterisk. So this is a chiral carbon which is having 4 different groups attached to it: A, B, D and E. So in short, we also call it capped. So capped is a chiral carbon or asymmetric carbon having 4 different groups attached to it. When such a situation is there, so you can compare it to our 2 hands, left hand. You can compare it to our left and right hand. As you see right hand and you see left hand. So these are mirror images. These two hands are mirror images, and you can see if I bring this over this, you can see that my thumbs point in different directions. This phenomenon is called non-superimposability. Had we been having this position, we would say that these are superimposed. But here you see that if you bring it over this hand, if you bring right hand over your left hand, then your thumbs point in different directions. So this phenomenon is called non-superimposability. So in case of mirror images, these two mirror images are non-superimposable. So this is a necessary condition for optical isomerism. Now if we don't have dissimilar groups, then we will not have non-superimposability. For example, if we have this carbon, and this is having A and D and E. So you see A, D and E. When you put it over this, so this is like having something like this. So both are symmetric, and if such a thing is there, if you bring it over this, then you will get a superimposition. So this, in case of optical isomerism, there should be an asymmetric carbon or chiral carbon, so that mirror images should be non-superimposable. So this is the essential condition for optical isomers. Second thing is number of optical isomers. According to Liebel and Van 't Hoff rules, the number of optical isomers that you can have is given by 2 raised to the power n, where n is the number of chiral carbons. So if you have one chiral carbon, then you get 2 to the power 1, that is 2 optical isomer. If you have n is equal to, if you have 2 asymmetric carbons, then you will get 2 raised to the power 2, means 4 optical isomers. If you have 3 chiral carbons, then you will have 2 to the power 3 is equal to 8 optical isomers, and so on. Now come to this point. When we have more than 2 optical isomers, then 2 will be mirror images of each other, but the rest will not be mirror images, but they will be optical isomers. So in that case, those two which are optical isomers as well as they are mirror images, they are called enantiomers. And those optical isomers which are optical isomers but are not mirror images, they are called diastereomers. So next we will see this phenomenon in case of monosaccharides. That is, first we will see it in glyceraldehyde, and then we will see it in other higher monosaccharides. So first let us talk about the optical isomerism in simplest hydrocarbons. As I told earlier that there are 2 compounds. One is glyceraldehyde, which is the simplest aldose, and another is dihydroxyacetone, which is the simplest ketose. Both these carbohydrates are simplest in the class, and let me tell you that dihydroxyacetone is the only carbohydrate which is not optically active, and glyceraldehyde is optically active, and all the rest of carbohydrates are optically active also. So here we will see optical activity in glyceraldehyde. As you see, the formula of glyceraldehyde is CHO, CHOH, CH2H. So this is a 3 carbon carbohydrate. This is triose. So in this, if you see, so this carbon 1, this carbon 2, and this is carbon 3. So if you see, this carbon 2 is chiral because it is having 4 different groups attached to it. One is H, OH, CHO and CH2H. So because it is having an asymmetrical or chiral carbon, so it conforms to our criteria of optical isomerism. So in this case, we should we should get mirror image. So if you draw a mirror image of this, you get this. So here you see that both these two forms of glyceraldehyde are mirror images of each other, and because they have asymmetric or chiral carbon, so they ought to be enantiomers of each other. So one of this is called, in which if you see the orientation of H and OH, in this form H is on this side and OH is on the other side. So this form is dextro-rotatory. This is dextro-rotatory, and this is designated as D-glyceraldehyde. And this other form, it is levo-rotatory, and this is designated L-glyceraldehyde. So it is understood that D-glyceraldehyde rotates the plane of polarized light towards right, whereas L-glyceraldehyde rotates the plane of polarized light towards left. Now we will see the same thing in higher forms. Here you see optical isomers of monosaccharides having more carbons than glyceraldehyde. So here glyceraldehyde had three carbons. Out of this, one carbon was asymmetric, so N was 1. So in this case, number of isomers was 2 की power n means, that is 2 की power 2 isomers, and 2 isomers were D-glyceraldehyde and L-glyceraldehyde. Now we increase the number of carbon atoms. Here you see 4 carbon sugars, 4 carbon monosaccharides. In this case, there are 2 chiral carbons, 1 and 2 chiral carbons. So if there are 2 chiral carbons, so N is equal to 2, so it means 2 power 2 means 4 isomers are possible. Here we are only drawing the shapes of D isomers. So here you see D erythrose and D threose. Similarly, if we have 5 carbon sugars, so in them there are 3 chiral carbons, 3 asymmetric carbons. So if N is equal to 3, then it means 2 की power 3 means 8 isomers. Out of this, 4 will be D forms and 4 will be L forms. So here you see 4 D forms, and lastly we are having hexose sugars. So in case of hexose sugars, you have 4 asymmetric carbons. And in this case, we can have 2 to the power 4 means, you see, N is equal to 4 means 2 to the power 4 is equal to 16 isomers. So 16 isomers are possible for hexose sugars, out of which 8 are D isomers and 8 are L isomers. Here you see the shapes of D isomers. See the drawing of these shapes is very simple. You start with D-glyceraldehyde and then you add one more carbon, one having this orientation similar to D-glyceraldehyde, and other is having opposite orientation. In next line, you take this shape and then you add one more carbon, one in this orientation with H here, this on this side, OH on this side, and the other in opposite orientation. Similarly, you do the same for this shape. And in the next row, you take this chain and add one more, one in this orientation with H on this side and another H on the other side. So that's you do the same thing for all these 4 forms. So you get 8 D forms for hexose sugars. And now I wish to explain a very important thing about monosaccharides, and that is sign convention. And this is something that confuses most of the students. So let's clear this confusion here. As you can see that in glyceraldehyde, I explained that D-glyceraldehyde is having the orientation of H and OH on penultimate carbon like this, and D-glyceraldehyde is also dextrorotatory, whereas L-glyceraldehyde is having, because it's the mirror image of D-glyceraldehyde, so it's having the orientation of H and OH on penultimate carbon opposite to that of D-glyceraldehyde, and this is levorotatory. So in case of glyceraldehyde, D is also dextrorotatory and L is levorotatory, but the same thing is not true about other carbohydrates, and we have different notations for dextro and levorotatory than we have for D and L forms. So what means D and L and what means dextro and levorotatory in the context of higher carbohydrates, you should clear this doubt here. See, in higher monosaccharides, D and L designations do not stand for dextrorotation or levorotration. Instead, D forms are all those forms which are having the orientation of H and OH groups on their penultimate carbon, and penultimate carbon is the second last. Penultimate carbon means second last. The orientation of H and OH groups around penultimate carbon is what matters the most. So if this orientation of H and OH group on any sugar is like that of D-glyceraldehyde, then that sugar is designated D, and if it is like this, then it is designated as L. So here we see that both these sugars, this is having 1, 2, 3, 4, 5 and 6 carbon. Here also 1, 2, 3, 4, 5 and 6 carbon. So which one is penultimate carbon? The second last. So fifth carbon is the penultimate carbon. Here you see that in both these cases, the orientation of fifth carbon, the penultimate carbon is having the orientation of H and OH group similar to that of D-glyceraldehyde. That is why both these are designated as D sugars. This is D-glucose and this is D-talose. But you can see this D-glucose, whereas this D-glucose is written as D plus glucose. Talose is written as D minus talose. So what this plus and minus indicates? This plus indicates dextrorotation, whereas minus indicates levorotation. So this is simple. Here you see that if H and OH are in this orientation, they turn the plane of polarized light towards right, and if they are in this orientation, they rotate the plane of polarized light towards left. So why this is plus? Why this is dextrorotatory? Here you see this group is rotating the plane towards right. This group is again in the same orientation, it is turning the plane of polarized light towards right, and again this one is also turning the plane of polarized light towards right. So you are having three groups which turn the plane of polarized light towards right, and this one is rotating the plane of polarized light towards left. So three groups are rotating the plane towards right and one is rotating it towards left. So the overall rotation is towards right. That's why this compound, that is D-glucose, ought to be dextrorotatory. Its overall rotation ought to be dextrorotatory, and that is why we designate as plus. So D-glucose is written as D plus glucose. And now here you see talose. This is 8D sugar. As you can see that the orientation of H and OH groups around penultimate carbon resembles the orientation of D-glyceraldehyde. So that is why we designate it as D sugar. But if you see that this group is rotating the plane towards right, but the other groups, this group is in this orientation. All the three groups are in opposite orientation to this. So these three groups are rotating the plane of polarized light towards left. So here you have one group, one carbon dextrorotatory orientation and three carbons having levorotatory orientation. So overall rotation is levorotatory. So even though this is D sugar, but it is minus, means it is levorotatory. So now it should be clear to you that D and L, capital D and capital L in case of monosaccharide do not stand for dextrorotatory and levorotatory. This is a big confusion among students. Instead, we have plus and minus designation to indicate the plane of rotation, means dextrorotatory and levorotatory. Sugars are represented by plus and minus sign, not by D and L sign. At this juncture, it will be quite useful to understand RS system for designation of sugars, which is a substitute to the DL system that we just saw with reference to certain monosaccharides. As we saw that DL system was originally proposed to correspond to the direction of orientation of plane polarized light, and D was supposed to be dextrorotatory and L was supposed to be levorotatory. However, as we saw that this correspondence, although this holds in case of glyceraldehyde, because D-glyceraldehyde is dextrorotatory and L-glyceraldehyde is levorotatory, but the correspondence does not hold in case of higher monosaccharides. For example, we saw that in talose, it is D-talose, but it is levorotatory. So a D sugar may be dextrorotatory or levorotatory, or an L sugar may be dextrorotatory as well as levorotatory. So it gives rise to some confusion. So this is a problem with DL designation. Besides, whenever we propose a DL designation, it is always with reference to certain molecule. For example, in case of glucose and means other monosaccharides, it is with reference to glyceraldehyde. So in order to overcome this shortcoming, this RS system has been proposed, which is not given with reference to any chemical. So it is absolute in this sense. So what we consider in giving this designation is the hierarchy of molecules, hierarchy of groups attached to the chiral carbon. So in assigning R or S, we only consider the hierarchy of groups attached to the chiral carbon, and it gives the spatial stereochemistry of molecules. So it is absolute in this sense. Here I explain RS system with reference to D and L glyceraldehyde. What you see here is a comparison of DL and RS designations. As explained earlier, in case of glyceraldehyde, you can see this is D-glyceraldehyde, which is dextrorotatory, and this is L-glyceraldehyde, which is levorotatory. Now we can assign R and S designation to these forms, and when we do so, R glyceraldehyde is equivalent to D-glyceraldehyde, it is equivalent to D form, and S-glyceraldehyde is equivalent to L form. While designating R and S structures, what we do, we consider the tetrahedral structure of glyceraldehyde. So think of this tetrahedral structure and keep the group with least priority. In this case, hydrogen is of least priority. So we point this away from us, and then we see the orientation of the remaining three groups. When H is pointing away from us, the remaining groups are OH, CHO and CH2H. Now we see that they fall in this hierarchy. OH is higher relative to CHO, and which is higher related to CH2OH. So if we see the hierarchy, So it goes in clockwise direction. So when H points away, means hydrogen which is of least hierarchy points away, and the priority of remaining group decreases in clockwise direction, then we assign R designation. And when it is the opposite of this, means when H is pointing away and priority of groups decreases anti-clockwise, as you see the OH, then CHO and CH. So this is this priority is decreasing in this direction, means anti-clockwise direction. So then we assign S designation, and as we can see, R glyceraldehyde is equivalent to D form and S glyceraldehyde is equivalent to L form. So in a way, RS designation is superior to DL designation, but assigning R and S in more complex carbohydrates is tricky and complex. So DL designation is more popular in the literature. Now we come to a very important part of our discussion that concerns various structural representation of monosaccharides. See, monosaccharide sugars can be represented in several ways, and a clear understanding of this concept is very important in drawing complex sugar structures. So we have both open chain structures as well as closed chain structures for monosaccharides. So let us start with the simplest form, that is molecular formula. Here I am illustrating this concept with reference to glucose, which is a hexose sugar, as you know. So for glucose, this is the molecular formula, and this is the simplest manner in which glucose can be represented. And now, as I explained earlier, that glucose molecule is having one aldehyde group and four hydroxy, five hydroxyl groups. So this information, if we incorporate this information, then we get this structure, which is called Baer-Fittig or Fittig-Baer structure of glucose. But in this, we don't get any idea of the orientation of H and OH group. As I explained earlier, that the orientation of H and OH group around chiral carbon is very important in any structure. So if we incorporate that information also, then we get this structure, which is called Fischer projection. That is very popular. So Fischer projection formula for glucose looks like this. So as you have seen earlier, in this is carbon 1, means functional group CHO, then carbon 2, then 3, carbon 3, then carbon 4, carbon 5, and then carbon 6. Again I will remind that the orientation of H and OH around penultimate carbon in case of glucose is fifth carbon, means second last carbon, is like that of D-glyceraldehyde. So this is D-glucose. So this structure is for D-glucose, and in this you can see the orientation of second, fourth and fifth carbon is similar, and the orientation of H and OH group around third carbon is different. So this is Fischer projection, and in shorthand notation we skip writing this C. So we get this shorthand notation for glucose. So this is shorthand for Fischer projection. So we will be using this form very frequently. But this open chain structure has several problems. It fails to explain several properties of monosaccharide. So we have closed chain structure also, as I explained here. After open chain structures of monosaccharides, let us see closed chain structures. Although Fischer projections that I just described are useful in explaining several properties of monosaccharides, but they fail to explain certain properties. So before understanding the closed ring structure, we have to take into account this important reaction, that is called hemiacetal and hemiketyl formation. As you see, whenever an aldehyde reacts with OH group, it forms this thing which is called a hemiacetal, and if it further reacts with another molecule of alcohol, then this thing is called acetal. Similarly, if we react a ketone with an alcohol, then it forms a hemiketal, and on reacting with another molecule of alcohol, it forms a ketal. So hemiacetal and hemiketal are formed when an CO group reacts with alcohol group. So this concept is very important in understanding closed ring structures of monosaccharides. Here you can see how this hemiacetal formation give rise to ring formation in glucose molecule. As it is shown, an open chain glucose molecule on closure of chain can either form a pyranose ring or it can form a furanose ring. This is pyran and this is furan. So pyranose ring resembles this type of structure and furanose ring resembles this type of structure. So when a pyranose ring is formed, then carbon 1 of glucose molecule forms a hemiacetal with 5 position, carbon 5, and this either this or this structure results. So one is alpha D glucopyranose and second is beta D glucopyranose. So in nature this is most abundant form, and 62% of the glucose that we have is beta D glucopyranose, whereas alpha D glucopyranose form 37% of total naturally occurring glucose. Similarly, if the ring folds by linking of carbon 1 with carbon 4 of glucose molecule, then a furanose ring results, and again it can be either alpha D glucofuranose and or it can be beta D glucofuranose, which are least abundant in nature. In this you can see this structure can be easily represented in this form, and this ring structure is called Haworth structure. It is named after a biochemist Haworth. Another important thing to consider in the context of ring structures of monosaccharides is the formation of anomers. As you see, that formation of closed ring structures creates another center of symmetry in a monosaccharide molecule. Here, for example, you see glucose molecule in open chain structure. Once it forms a closed chain, then this carbon 1 becomes a center of symmetry, and the orientation of H and OH groups around this carbon may assume two forms. In this it is alpha D glucopyranose, and in this form it is beta D glucopyranose. As you see that the orientation of H and OH groups around this carbon 1 is different in these two forms. So this carbon 1 is called anomeric carbon, and these two forms are called anomers. So alpha D glucose is an anomer of beta D glucose. In fact, anomeric carbon is the carbon that bears the carbonyl group. So it's not always that C1 will be the anomeric carbon. C1 is anomeric carbon in case of glucose, because the functional group of glucose is carbon 1. CHO group is on carbon 1. But if you see fructose molecule, CH2OH, CO, and then this is carbon 1, 2, 3, 4, 5 and 6. So in this case of fructose molecule, the carbonyl group is at position 2. So in case of fructose, C2 is the anomeric carbon. Thus anomeric carbon is the carbon of carbonyl group. Lastly, let me tell you about another important phenomenon related to monosaccharides, and this phenomenon is called Muta Rotation. It was observed by Dubrun-Fort in 1846 that when a pure form of alpha D glucose or beta D glucose is kept for a while, then its specific rotation changes and an equilibrium mixture is formed with a constant specific rotation. For example, in case of alpha D glucose, as you can see, the specific rotation is 112.2 degrees, and in case of pure beta D glucose, this value is 18.7. But whenever alpha D glucose or beta D glucose in pure form is left for a while, then this specific rotation reaches an equilibrium value, that is 52.7 degrees. So this phenomenon definitely it occurs because of interconversion of alpha D glucose and beta D glucose, and this is called Muta Rotation. So this is one of the important properties of monosaccharides. In the next video, we'll talk about various chemical reactions of monosaccharides and oligosaccharides.